So let's start reading these examples. In these examples from our week 11 lectures, we have to find the capacity of 175 by 50 F11. So what is 175 by 50? So if I draw this timber, and by the way, these are the standard size that is available in our Australian market. Like a one steel tables, there is also catalog for that 175 millimeters. So that is the size, and the grade is F11, and that grade is just how the young modulus, how stiff your timber is, and it's an unseasoned hardwood. It's going to be used as a principal columns. Principal columns is the primary members, main columns. If these columns break, most of the structures has a significant effect. And generally speaking, the columns are the primary members, because you can think of, if the columns break, you generally have a significant effect or significant failure in your structures, unlike beams. Supporting a floor in a salt storage facility near Karawan in Western Australia. So basically, it's a storage facility and it's in Western Australia. That will help you for some of our K factors. Connection will be made by M16 bolt with the 2 bolts per row. So as you know, the columns would be connected at bottom and top end of it, that one. So how the connection is been, they are screwed with the M16 bolts. They already work out the critical design loading, which is, they say that only permanent loading is the critical for our case. As you can see, this is a storage facility, so live load would not be critical, because you can see in storage facility there are not users. You don't have a party in your storage, in the storage, right, in the warehouse. So you know, you're going to store the heavy materials in that storage facility rather than the user. So only workers are using that facility. So the storage is the critical one. So therefore there is a permanent load. That is logically makes sense, right? Length of the member is given 3.6 meters. So if it is, if we have a columns like this, so that is 3.6 meters length given, and this is how much, 50, and that is 175 given here, with the restraint at the third point in the minor axis direction only. So minor and major axis. So this is your let me help you out with this one as well. So let's say just put the y-axis, and let's put this x-axis here, and this x-axis would be your major axis, and the y-axis is your, you don't need to remember that, is a minor axis. Okay, so that is I will show you how you can get it. So you have only restraint in the one direction only, about the minor axis. So you have a minor axis here. So about the minor axis that you can see, which is the x-axis, in that case you will have a restraint going like this, restraint 1, restraint 2, and there is a restraint 3 at the third point. So that's prevent this minor axis bending. And on the other side, major axis, you don't have anything. It's like as you can see, where is my rulers? Okay, here you can see here you can see this. You can see these rulers, right? This rulers has this cross sections, rectangular cross sections. One dimension is very thin, another one is very wide. Now, if you have this ruler, and this is a columns, you can see these columns, right? And if I bend it, look, it's very easy to bend, very like a slide, easy to bend, right? This is let's say this, if I put it this way, now this is called the minor axis bending, right? Because you can see this is why minor, it's not majors, right? Or you can say weak axis. Sometimes they call it weak axis as well. So y-axis is a minor axis. You can see these cross sections here. Y-axis, you can easily bend this way. If I want to bend about the major axis, it's very hard. If you have something in your, if you have a rulers, you can experience yourself. It is very hard to bend about this way. There is a reason for that. if you look at this axis and the materials distributed about this axis is more. Oh, sorry. If you see this axis like this axis, like this, my finger is axis. So the materials which is distributed from this axis to this end is too much. It's hard, so it is very difficult to bend. And if you see this axis, tiny bit of axis, and the material distributed about this axis is not that much, so you have easy to bend. So there is a so if I have a, in my garage you have a extra timbers, and if I want to restrain these columns, I would restrain against this bending, because this is already strong. So if I want to increase the capacity, I want to increase this one. So in that case, I put the restraint like this. I put the restraint like this, then I can't bend it, right? If I put the restraint like in my finger, and I put the restraint here, it's going to be difficult to bend. You can see this is difficult to bend. You can see they need to bend. So I will put this restraint. This is a minor axis restraint. So if I put that restraint, let's say my fingers, these are restraint 1, restraint 2, and if I apply the load from here, it would be difficult because I'm holding it. Look, it's not going to be easy because I'm holding it in here. So it will not do this one because it will have these, and these. So it's significantly increased. I hope you understand that. So if I put the restraint here, it will going to do this one. So that is not good. So you need to have a minor axis restraint. I hope you understand that. So that is the, of course, we're going to discuss it in the details. Now let's dive into these examples. Now, if you remember, last week we used 3.2 beam design. There was a 5 case that we discussed: K1, K4, K6, K9, K12. I also explained 5, FB dash, bending strength, and Z. Right? So you remember that one, right? You remember that if I have something, you remember that if I have a timber beam and I bend it means, let's say, just apply the loading and then it will bend. It will bend like this, right? So in that case, you have a neutral axis and the bending stress that you're going to get in that cross sections. Let's say I draw this cross section here. The bending stress is like this: tension and compression. That is your bending stress, sigma B. And sigma B is equal to my on I. Y is the distance from neutral axis where you want to find the bending stress. That's the moment, how much moment you need to bend it, right? So if I have this ruler and if I want to bend it, this is the moment, M, how much moment I am applying it, right? And if I want to calculate the stress, sigma B, my on I, the moment of inertia, the distance y, and the moment. So that's we cover it, and then we say that, okay, this does not sounds good. So as we know, M is equal to I over Y, and I over Y is the section modulus, M over Z. So the standards is give you this one. I think the standard is giving you MD, FB, and Z. So that's okay. They say that this sigma B is your FB dash, that is a bending stress. This M, they said it is MD, and that is your Z. So if I want to calculate the moment, it's just FB dash Z, right? That's we done. And this one all are based on the timbers. Like you have a high temperature, you have a moisture, you have a local global buckling and low duration and so on, right? You remember that one. So this is the equations. But now the scenario is different. Scenario is different, meaning that you have same timber. This one that I show it to you. You have same timber, and this time I am going to squash it. I am going to press it like this. So in that case, these equations, which is sigma B, let's say sigma A, let's say axial stress. This is your bending stress, right? We done it last week. This is your bending stress. That's okay. Now, if I want to calculate the axial stress is equal to how much load you are applying it, at both ends, and where you are applying, how much area that you are applying. That is axial stress. Simple, right? So the standards recognize that simple things. 2.3 plus 3.2 bending, that's okay. We going to go few pages down here, And we're going to say that close 3.3 is a column design. Looks good. NDC is equal to FC dash and AC dash. What is this one? So let's work it out. That these standards is telling me that this axial stress is FC dash. The stress is FC dash, compression stress. Compression stress in the timber FC dash. That is same like your axial stress here, that's sigma A. That's okay. And standards also give the different name for load, that is NDC. So that's okay. Let's put NDC here. And the area, standard is telling me that area is equal to AC. Okay, that's fine. We can put the AC. So NDC equal to FC dash times AC, right? That is the equation here. That is the equation here, and NDC equal to FD dash, basically force is equal to stress times area. Someone might say, people, what is these 5 different guys? Okay, those 5 things are just going to be help us, some are not going to help us. But if you are sitting with the architectures and within the 1 second, let's take a 5 seconds, you want to know the capacity of the team. Well, that is not accurate. Look, this will not give you the picture, but you know, look, these guys here, they will reduce your capacity somehow, 30%, 40% somehow, we don't know, but they will reduce. Okay, but if you really want to, in your exams, you are sitting and you want to calculate the capacity or NDC without looking the standards, you have a mechanics of solid knowledge, you can straight away calculate that one. Forget about all this one that's you don't know. Okay, you can easily calculate that one. Okay, but then I also teach you this one, but this is the basic things. The standards follow exactly the basic stuff. So that is just force is equal to stress times area. So there are different terminology, therefore it looks different. So standards wants that the capacity of your sections would be higher than the NC dash, which is your design axial force. So they said, okay, your column compression capacity should be greater than design axial compression. That's what it says. Yeah, to be secure, NDC should be greater than or equal to N star, right? That's okay. Now, standards also wants to calculate NDC, which is given in 5, K1, K4, K6, K12, FC dash, AC, where is given in the clause 3.3.1.1, right? I can show it to you here. Clause 3.3.1.1, NDC 5, K1, K4, K6, K12, FC dash AC. Let's work in the sequence and work out each one. So the first one, 5, is called capacity reduction factor. Capacity reduction factors. How do we gonna get that? 5, I think you know the bending one, the same one that we're going to use it. Did they say that? Yeah, capacity factors close 2.3. So the same tables that we use in that one, close 2.3 is close 2.3 capacity factors, and is a reduction factor, so less than 1. So you have a table 2.1, you have table 2.2. Table 2.1 is used when you're designing the member. Table 2.2 when you're designing the joints. In our course, we are not covering the joints, so we are not going to use table 2.2. Only we're going to use table 2.1. How are you going to read this table 2.1? You have given category 1, category 2, category 3. I think it is a revision for you, but I will remind you again. Category 1 is quite simple. It's based on the risk base. Risk base means this is less risk to the users, this is a more risk, and this is the severe risk for the users. Category 1, meaning that you have a secondary members, meaning that if that members that you are designing is failed, only 25 meters square unlikely to affect an area greater than, so only up to 25 meters square of area will be affected. If you have 5 meters by 5 meters room, then you only that area is affected in your structures if that members fail. That is category number 1, or you can say is a secondary member. Category number 2, when you are designing the primary member of your structure, if that member fails, more than 25, maybe 2-3 bedrooms are damaged, right? In that case, you are in the category number 2. Category number 3 is a severe meaning that you have police station, fire station, hospitals, where, okay, give me minutes, I will just put these blinds down. So category number 3, where you have a structures which is post disasters, like in that disaster situations, they need to be secured, right? If they have a damage, then they are the helpers. They need to help the community, like a fire station. So in that case, if the fire station has a structural failure, they can't go and help to the others. So in that case, they have a severe penalties up to 40, up to from 25 to 40% penalty applied. Here you will have up to 10% to 30%, 10% to 30%, and here 5 to 10%, very small penalties. Okay, here how you going to read it? There are different grades that you can use it. If you are using the low grade, you can have a, if you are using higher grade, like higher grade, you have small penalty. If you are using the small low grade, you have a higher penalties. So in our example, so I hope you understand these tables. Any scenario given to you, you should be able to read that capacity factors. Now in our example, it says that is the principal columns. Principal columns meaning it is a primary members. So if you have a primary members, let's get the table 2.1, and it is a primary member. And what was our grade? Our grade is F11. Where is F11? F11 is given here. So it's F11. So that is the useful information. Go back here. Is a primary members. Yes, it is a primary members, primary structure members. So category 2. Let's write it down. It is a category 2. Category number 2, F11, stress F17, all other timbers and stress grades. So we have a 0.7, 30% penalty are applied. So you have a 5 equal to 0.7 coming from table number 2.1. Unmute yourself if you don't understand to get these capacity reduction factors. Not only this scenario, but any scenario. Unmute yourself that you don't know how to read these tables, like how you going to scan these tables for any scenarios that would be given to you, right? No response, meaning that everything looks okay. Now let's move on. K1. Now what is the name of K1? Let's write down the name of the K1 first. Now the K1 we call it, look, this is all called modification factors. If I don't mention that it last time, it is called modification factors. All these case, the name of this case, if I combine all of them, it is called modification factor. Modification factors. Of course, each factors has a specific name, and that is given in the clause number 2.4. Of course, it has a specific name, but if I group them, then this group is called modification factors. Now for particular K1 is called duration of load factor for strength. Let me write it down. Duration of load factor for strength. Now you have two options to get this K1. Option number 1, you can have table number 2.3. Table number 2.3, or that is table number 2.3 is here. I will explain you both options, okay? And or you can go to the appendix G, or you can go table G1. I will explain you both scenario. And then or you can have a table G1. Now this These tables, which is table 2.2, has a effective duration of peak actions. Okay, so you have 5 seconds, 5 minutes, 5 hours, 5 days, 5 months, 50 plus years for the strength of the timber, for strength of the joints. So we don't worry about the joints. These columns we don't worry, just we're going to worry about this one. Now what is this one? What is this 5 seconds, 5 minutes, 5 hours, 5 days, 5 months and 50 years? Now this duration, that is the probability. Look, this, no one has a perfect answer for that one. This is the probability that your members will have that ultimate strength will be experienced over the life of the structures. Like if you are a storage facility for 50 years, it does not mean that you already take 50 plus years. 50 plus years meaning that during the whole period of the 50 years, your structures will be having ultimate strength all the time. Because you see, in the storage facilities, you might have a, at some stage, let's say Christmas time. In the Christmas times is a busy period. You have to store significant amount of items that is in the warehouse. During the quiet time, which is not, let's say, in the winter time, you don't have too much shopping, so in that case you have less dead loads. So during the whole year you may not be able to say that okay, you have in some scenario, yes, if your architectures or your client mentions that okay, your structure is sensitive and they have this loading over the life of, and then you can go here, there is no any issue. But typically we take it these 5 days, 0.94. If you don't know normal structures like the house and storage facility and all, we go for this 0.94. That is typical 5 days normally, generally, not a special case. Like wind load and all, we just 5 seconds and all this very small amount. This is very small. So that's we don't carry, but generally we take it 5 days. 5 days meaning over the life of the structures, you have 5 days where you're going to reach that ultimate point. And look, this is quite, still 5 days is quite high. It's not, your structures will not going to experience those kind of things. So 5 days generally we take it. That's how you use the table number 2.3. Now table number G1 has nothing to do with the period, but it has different load case. Different load case meaning that your structure has which loads. Look, in the real world, you need to analyze all the load cases and you need to pick the severe one. So this timber example which I am showing you, you need to do it for here, you need to do it for here, you need to do it for here, you need to do it for here. So you need to repeat this example for 1, 2, 3, 4, 5, 6, 7 times. Depending, sometimes the earthquake wind loading is not severe, your client doesn't want that, then you can eliminate that. But saying that okay, you have dead load, live load generally, then you need to do all the load cases, and then you pick the critical load cases. In our examples, it already mentions that you only need, they already done the work for us and saying that this is your critical load case. So in that case, we can just straight away take this 0.57 in our examples, that okay, the only, so look, dead load is, only dead load is very bad, because your dead load is constant. It will be there for all the time, right? You can't just ignore it. Like unlike here you have dead load and live load, but here 1.35 constant, 0.50, so quite significant penalty is applied here. So how you make a decision between this and this? Again, you need to, in the real world, you need to if in the examples it means permanent actions in the exam, then you just straight away use these tables. If they mentions that okay, design it for 5 days and all, you can read this from tables. Okay, but in case if nothing mentions, you can just go for 5 days 0.94 straight away. Okay, but in our case we have a permanent actions. I can show it to you where it is written. In our examples, it's written here, permanent loading only. So in that permanent loading case, we will just going to say that is a permanent loading, and for permanent loading we are going to use table G1, which is 1.35 G, and for that table G1, we take K1 factor 0.57. So in that case, we take K1 equal to 0.57. Now next one is K4. Now K4, name of that K4 is there you go. The name of is called partial seasoning factors. What is that? K4 is called partial seasoning factor. By the way, these factors are common whether you do bending or whether you do the axial. I will also going to compare with the bending. K1 and K4, they goes in the bending as well, and K4 is the bending, because look, if you have beam or columns, it will be loaded for duration, so it's, you can't just ignore that one. K4, if you have a timber column or beams, you still have a moistures in that scenario, so you need to have a that factors. Okay, now they mentioned something here in our examples, that in that examples they said that is unseasoned hardwood. So in that case, if it is unseasoned, for unseasoned timber, generally K4 equal to 1, where the unseasoned timber is used under normal condition of temperature and humidity and will not be subject to full design load until it's partially seasoned to below 25% moisture. It is permissible to increase the characteristic unseasoned timber by multiplying these factors. We did not mention anything that 25% moisture content and so on, so we just take K4 equal to 1. It's basically saying that if unseasoned timber, it says that, okay, look, unseasoned timber meaning you have a moisture in that timber. When the seasons, you take the moisture out. Moisture out meaning when you take the moisture out, timber gets stronger. Like you can think of when the timber drying it out, it gets stronger. So therefore it has more than one value. Look at that. Like you can have 15% increase, 10% increase, 5% increase. K4 will sometimes help when you're drying out your timbers, right? So, but I think in our example it says unseasoned timbers, meaning that we have a moisture in that timbers, so we just these factors can't help us. Okay, so therefore we have K4 equal to 1. But in case if we drying it out, then in that case the K4 could be more than 1. It can help, it can boost up your this one. So K4 equal to 1 because we have unseasoned timber, and the detail is in the clause number 2.4.2.2. So unmute yourself so far if you don't understand these 5 reduction factors. K1 like load duration factors, and K4 is kind of what we call partial seasoning factors. It's not only for this scenario. If you have any scenario like in the examples, if you have given this equilibrium moisture content, then you can just plug the value and you can find the K4 values. Okay, so it's quite simple in that scenarios. Let me work it out, this one scenario for you. Let's say I have yeah, so you can see that let's say moisture content is given to you is 25% moisture content is given. Let's say 25%. Okay, that is a scenario that EMC is given 25%. So how are you going to calculate 25? Just don't convert, divide by 100. Just straight away put 25. This is in percentage over 15 divided by 10. So it's 1. 1 times 0.3 is 0.3. 1 take away 0.3 is 0.7. Yeah, 0.7. So you need to calculate 10% between these values. So there was some kind of all right. So this EMC like 35%. If I get 35%, so 35 you take away 15 divided by 10 times by 0.3. So 1 take away 0.6, you get 0.6. So in that 0.4, in that case you can take the 0.7. So you can just take a maximum value out of it. Okay. So K4 done. And now we have K6. What is that K6 called? Now the K6 is called temperature factors, close to 0.4.3. Close to 0.4.3, K6, it is called temperature factor. Now in that temperature factors, if you have your timber sitting in the north of Queensland, like on this one, or you are in the Darwin, on those regions where you have this map. I think I have these standards. I think next year we're going to teach you these standards, but I can show it to you here. This is the concrete standard, by the way, AS3600. Next year, these times you will going to take that subjects. In that standards, they have give you these figures. I think that you don't need to worry about it, by the way, for this. And someone might say, in the exam, should I take this standard as well because I don't have maps and all? Oh no, this is just for your information. Look at this. They put this hex line, that is a tropical weather. Tropical weathers B1, like this one is a tropical means heavy rainfalls. You can see this map is given the Bureau of Meteorology. This area have a heavy rainfalls. This area horizontal line is temperate, is a moderated rainfall. You have moderated rainfall in the Sydney and Melbourne regions here. Here in the middle is arid. You have a very little no rain kind of this region. Here again you have temperate. You have moderated rain. So if your timber sitting somewhere here in this rainy zone or in the high temperature, then your close this one will come into the pictures. Other than that, because it's just altitude and these latitude things that you can think of. So that's the quick update. It's basically our timber is in Western Australia. I can show it to you here again. Our timber is in, yeah, I think our timber is in Western Australia in this region. So we have a very low rain region here. So arid is having little or no rain. So our timber will not have a water from the outside. So I think I can show it to you here that here it should be in Western Australia, and that K6 equal to 1. Right. So and that is in the close to 0.4.3 because our timbers is in the Western Australia. All right. So K6 done, quite easy. K6 done. Oh, K12 is kind of require a bit of attentions, but I will take you through the details. So any scenario you come, you should be able to read the K12s in any scenario. K12 was, look, don't confuse here. You have a K12 for bending as well, but this K12 should follow from close 3.2.4. So close 3.2.4 meaning that here stability factor, this is called stability factor. So don't come here when you're designing for the columns. Okay, this is for bending, by the way. There are two K12, one for the bending and one for the, well, this K1 and K4 and K6, they are same, either is the beam or columns. There is no separate close for beam and column. But here for K, we don't have K9 in the columns, but we have K12. We have a separate close for that one. For beam you use 3.2.4, but for columns you don't need to remember that, they already mentions disclose here, close 3.3.3. and see the modification factor section 2. So close 3.3.3 here, close 3.3.3 here, stability factors, again the same name, 3.3.3 stability factors. They have given you this close, don't get from here. Okay, if you want to make a note yourself, 3.2.4 for bending, don't take it from here when you're designing it the column. So columns should be here. So when you have a columns, it still have this global buckling kicking it out, like in the beam you have this lateral dorsal buckling. You remember that lateral dorsal buckling happening, and therefore we have this K12, this K12 stopping in the beam. Now in the columns it will happen again, right? This K12. So these K12s will tell that if you have happened this one, the standard don't like, we will get the penalty to K12. If your column is restrained and it does not have these problems, then your K12 would be 1, K12 would be 1, so be okay. Short columns or restrained columns, your K12 1. As your columns is getting long, like long meaning that the length is increasing without the restraint, your penalty is increasing. This is the intermediate columns or this is the long column. So you can say short column, intermediate column and long column if you want to read it like that. So in that case, we will find it out. Now, they are depend on this rho c. Like you remember that we have a rho b as well, material constant. This one rho b is similarly we have rho c, which is the material constant given here on table 3.3. As Heather mentions, they are depending on which grade that you are using it. It's also take into account this called initial curvature and so on, the creep and all. So they take into account this one. We have F11, so rho b equal to 1.02, right? Let's say K12 is called stability factor, and that is coming from the clause 3.3. And for that stability factors, we need to calculate rho b times S, and that's rho b is called material constant. It's called material constant. Now that material constants can be read from table number 3.3, and we have a grade. What is the grade? We have a grade F11. Now that F11 grade, we have a F11 grade. For F11 grade, rho b would be read as F11 1.02. Oh, on season timber, sorry. So in that case, you have 1.18 because we have given the on season timber. So we will to have a 1.18. So 1.18, and where is because is on seasoned timber, meaning that unseasoned timber here. So standard don't like unseasoned timber. They I think this factor is higher. So in that case, you might have this penalty higher, right? So unseasoned timbers is not helping here. Now this is 1.18. S, what is S called? Because we need to find this S as well. This S is the buckling about the major axis, and S4 is the buckling about the minor axis, and we need to take the S value, which is the let me check. The S value would be higher of these S3 and S4, right? So S value, we always need to take a check maximum of S3 and S4, right? So you need to, what is S3? S3 is the buckling about the major axis, coefficient for buckling about major axis. And by the way, major axis meaning that, because major axis does not make sense, the major axis meaning that is the x axis. X axis meaning that, if you still does not know, is a strong axis. Strong axis meaning it's difficult to bend, that is the major axis or strong axis. And S3 and S4, you don't need to remember that, by the way. What I am writing it, I will tell you where you can find this major and minor axis. Minor axis, minor axis, and that is y axis. You can call it weak axis, where you can just going to have a less resistance about the buckling. So these details are given here. Always you need to make it 2 checks. You have these slender coefficients for buckling about the major. So that is called slender coefficient, by the way. This is a slenderness coefficient, S3. Slenderness coefficient here. Slenderness is basically talking about how long your column is. Physically, it's telling me, it just wants to recognize how long your column is. All right, so now let's start moving on to this one. Now let me explain you this clause 3.3.2 to calculate the slenderness. So you have this page, this figures is useful, and there is a S4 given here. So there are 3 pages that you're going to go through it. Now it's required a little bit of attention. Please pay attention here with me. Now let's talk about the first. You need to do the both checks. You calculate S3 and you calculate S4 and you take the higher one, okay, the maximum one. Now again, S3 has 2 equations and S4 has 2 equations. So let's talk about that. Your beam will have a bending about major axis. Let's break it into 2 parts. Forget about when you working about minor axis. Let's say major axis. Major axis is your x axis. X axis meaning that is a strong axis. Meaning that let's work out the strong axis. It's very difficult to bend. Look, very difficult to bend, right? About this axis. If I'm talking about the real thin bar, there you go. In this one, if I want to bend, like this, it's okay. I can bend it about this axis. It's very difficult to bend like this. It's very difficult to bend like this. I can easily bend like this, right? Because you can see the materials distributions. If I draw the line here, the material distribution about this axis is a weak axis. Okay, this is the weak axis, y axis. X axis is a major axis. How you recognize that? The smallest dimensions. You have this is big dimension, smallest dimension. The parallel to that smallest dimension is the strong axis. You can say this is a strong axis. This is a strong axis. This is weak axis. Standard is telling me this is a major axis. The vocabulary of standard is the major axis. This is a major axis. This is minor axis. How are you going to recognize? They have written the word major axis and they have given the x here, right? That's how you recognize x, that x axis is a major axis. Now, so there are 2 equations. One is this one, LAXD, and another one is this one. Now, how you separate these 2 equations? Now, the first equation is telling me that when you have a restraint, then you have these equations as well. Of course, you need to do the both. But how they recognize that? That if you have a restraint, this is the dominant one. That if you have a restraint, meaning that you have a columns and then you put the restraint. And by the way, let me explain you the restraint. That if you have a columns like this, okay, and this is the strong axis, right? X axis, strong axis. In that case, if you want to put the restraint about the strong axis, let's say you want to put the restraint, let's say this bend this way, then you put the restraint here like this, right? You put the restraint like this. Similarly here, you have this, you bend about this way, you have put the restraint here, right? So that will stop to bend it. If I put the restraint here, I will not be able to bend it, right? If you not be easy to bend. So you put the restraint here. This is your, you need to put the restraint perpendicular to the axis. So this is major axis. You put the restraint perpendicular to that one. If I put the restraint here, that means it will stop bending this way. So in that case, you have this restraint about y-axis. Okay. So I hope you understand that major restraint. So this guys here is telling me that you have a restraint LAX meaning this distance from here to here. That is your LAX. These guys telling me that you don't have restraints. Let's say you don't have these restraints, but your restraint is controlled by these G13 factors. That is your end restraint. So sometimes you can have a restraint here as well. That will stop. If I hold it so tight, like a fixed one, then it's still difficult to bend. You can see that. You have pin, easy to bend, right? So sometimes you can control the restraint by at the end as well, like how you make the connections. That is recognized by G13. And by the way, G13 is called effective length factors, and that is come from here. Do you remember that K factors in the Euler's buckling equation? That is similar to this Euler's buckling equation. So you have G13 length, because as I mentioned, there was no restraint, so total length is that length. And you always take this dimension which is perpendicular to your axis of buckling. So you have this X, then you have this perpendicular is D, right? So that is always D. You remember that that's just information here. So I hope you understand these two equations. When you have restraint provided, you need to use both equation, by the way, because you says that you need to take the smaller value between these two. But I'm just telling you the physical meaning behind these maths, that how the standards wants to recognize that. Now everything should be explained, but G13 I did not explain. As I had mentioned, in the previous standards we have a figures, and look, this was quite challenging to understand, because there are 1 2 3 4 5 6 7 and 8 different cases. 8 different cases means how your columns is at the end. Is the top end is how, bottom end is how, and so on. So in that case, you have 1 2 3 4 5 6 7 and 8 different cases are given to us. Now for that case, I have these pictures will going to help us. There is a pictures that is going to help us, that how you're going to recognize that. Now in here you have a brace and you have sway. Now what is brace and what is sway? Look, the brace meaning that when your columns will be staying in that positions, right? Brace meaning that oh, SD1, you know brace, right? In SD1 I told you that brace one, but I remind you again. So brace meaning, let me explain that. No, this is not a good example. Brace meaning, let me brace and unbrace. So let's say you have these kind of a frame structures. Let's say you have this is called, let's say, brace frame, or sometimes they call it on sway frames or sway frames. Okay, in that case, let's say I apply the loading. When you apply the loading, these joints will not going to move from these original positions, but let's say it will have this kind of buckling issue there. But these joints, black one will not. That is called brace frame. And unbrace one, that is, let's say somehow, let's say I put some kind of wall, that's header mentioning, and then it's a brace, right? It cannot move, it cannot go under this loading condition. Let's say this wall is not there, then if I apply the loading, these points will going to move meaning they will just have this position change, right? And this guys is also going to do this, right? So I hope you understand. This is called sway frame. Okay, when your column does this one. So this is how it's going to be classified. Now in that case we have some cases which are brace, and there are 1 2 3 4 and 5 cases are braced. Brace meaning that your columns will be staying at that position, the two ends, and there are 2 cases which are sway, that your columns will one end will does this one. So let's read these tables along with this one. I hope you can see both ends. Now flat ends. So you have a flat end, so you have a 0.7. Let me read where is the flat ends. Okay, flat ends. So flat ends, both ends cut square to longitudinal axis and bearing on a hard surface. So you can see these are the kind of a flat ends. Okay, so you have loading here, and you have flat ends. So in that case, G13 is 0.7. So I hope you understand that flat ends. Now restraint at the both hand in position and direction. Look, this position is quite complex. I don't like this word position and direction. I like rotation and translation. So I replace these positions by rotations and directions. Let's say let me fully fix. So positions and direction, meaning that they are rotation and the translations, meaning that the rotation is prevented and the moment is prevented. So both are prevented. So it's like a fully fixed columns. Restrain both hand in position and direction. So you have both hand restraints in the position direction, fixed columns. You remember that in the Euler's bulking formula you have these fixed columns, like fixed columns. What would be your effective length and kind of that? So you have 0.7. So in that case you have G13.7, G13.7. So I hope you understand these two, and these two cases are brace columns because their ends are fixed. One end is fixed in position and direction, other restrain in the position only. So the on one end is fixed, fully fixed, right? Let me check that cases. So one end is fully fixed. Look at that. One end is fixed. It will not be rotated. It will not going to move, but it will other position only. Position only. So restrain in position. So it's position, but direction meaning rotation. Rotation is allowed. You can see this one, your this end will not going to do this one or this one, but it will going to rotate. So that is the case number, this which one, this fourth case, which have one end fixed. So bottom end, so this is basically bottom end is fixed, top end is pin. That's what the case is. So bottom end fixed, one end is pin, rotation allowed. Position meaning displacement, and the direction meaning rotation. So 0.85, 0.85. It could be top end or it could be bottom end. One end should be pin and another one is fixed. So I hope you understand those cases. 1, 2, 3, 4. So far all brace. Stud in the light framing, 0.9. Let me find that. Here, stud normally cut square and bearing on the timber top and bottom place. So if you have a stud and they are just screw nail, then you have this factor called 0.9. I hope it is makes sense. Framing 0.9. That is again brace one. Restrain at both hand in position only. Position meaning translation. So you have pin conditions, I believe. Pin here. You have two pins, both hand restrain in position. Position meaning this both hand cannot go up or cannot go down, cannot go horizontally, but it can rotate. So that is B one pin conditions, like this nail only. If I rotate this one, this nail will not going to provide the restraint. So that is one. That is again brace. Two more to go. Restrain one end in position, direction. So one is fixed, other end is partially restrained in direction but not in the position. There is a partial restraint, and this partial restraints meaning that you have this unbrace. This call is unbrace or sway. So one end is restrained in the both positions, so like this, and direction. So one end is fixed, but another end is going to do this direction but not in the position, both fixed but with sway. So this one fixed, but this end will going to have this kind of translation. Then you have G13 1.5. Restrain at one end in position and direction but not restrain in either position direction at other end. So two. So you have pin and you will have this translation, that is factor 2. So there are two cases which is sway, and those are all our 5 cases are brace. I hope it makes sense. Unmute yourself if you don't understand those things. So now I think we covered everything. Now we just need to drive into this just drive into this one because I'm running out of time now. Let's say we're going to talk about this S3 equal to LAX on D and S3 equal to G13L on D. Right, so that would be S3 would be minimum of this. S3 would be minimum of LAX on D or G13L on D. So let's do that. Minimum. Now G13 LAX, I think there was no restraint in the major axis. X is a major axis, and there was a restraint in minor axis only, right? So this is major axis, minor axis only restraint. So this is major axis. So there is no restraint, So LAX is your there is no restraints, meaning that this will not going to work because there is no restraint. As I mentioned, there is restraint or no restraint. G13, we can just find it out. G13 it out from here. We like to have each end held by two bolts substantially restrained 0.75, right? Because we have M16 bolt. And if I just show it to you in figure, like this, two bolts, and both ends held by two bolts, equivalent restraints 0.75, right? You can see that these are kind of by two bolts, kind of almost fix, but allowing some kind of like fix 0.7, but they just recognize that they're kind of slight rotation, so they just put 0.75 there. So that's helpful, two bolts. 0.75 G13, and by the way I can show it to you where they mentions these two bolts story. So they have connection will be made M32 bolts per row. So you have 0.75 0.75 G13, length 3600. You remember that length is there is no restraint, so that was 3600, and the D was, this is your small d, this is your B, so 175 is a D. Oh, by the way, I need to put one more details there. D is 172 millimeters. Why? Because I can tell you, because it's on-season timber. When you have on-season timber, generally speaking, over the life of the timbers, it will shrink by 3 millimeters. In that case, if you have 50 millimeters and 175 millimeters, after some times it become 47 millimeters. Look, it's not perfect. Someone might say, how do you know it's become 47 millimeters? No, just allowing the 3 millimeters clearance for on season timber. So this 175 becomes 172 millimeters. So in that case, you just have S3 value of 115.7. So that is good. S4 same scenario, but just replacing the B. And by the way, now we have restraint. So for that restraint case, we need to go for this end. So S4 is a minor axis buckling. Minor axis buckling. We have a this is with restraint, right? LAY on B. So S4 LAY on B. So LAY is here, and we have 3 restraints given. We have 3600 divided by 3. I think we have 1200, right? Because you can see that you have 3 restraint provided, blue one, and that 3 restraint is provided at a third point. So 3600 divided by 3, it gives me 1200 millimeters. So you provide the restraint at 1200 millimeters. So we have restraint at 1200 millimeters, and you remember that story about the on season. So you have 47 millimeters. So this will give you 25.5. So as you remember, S would be maximum of S3 is basically which one going to buckle first under this loading. So you have 15.7, which is major strong axis, and minor axis 25.5. So we will get 25. Still with the restraint, still this axis is the weakest one. And then we just going to multiply rho B and S. Rho B and S. Rho B was 1.18. 1.18 and S was 25.5. So 1.18 times 25.5, you get 30.09. If you have 30.09, in that case, come back here, 10 short columns, intermediate 30 is like a slender columns. We will have global buckling. So K12 is given here 200 over rho B as rho C S on S square. So this is not rho B, by the way. This rho B was before. Is it rho B I written here above as well? No, not rho B, rho C and rho C. Okay, this is rho C. All right, now so if you have a rho CS, which is rho CS is 30.09 is greater than or equal to 20, then in that case you can calculate K12 equal to 200 on rho CS square. It is given in the clause 3.3.3. So in that case 200, already we calculated this value, which is 30.09 square, which gives me, the calculations gives me 0.221. Right, now we have we have to calculate this two more parameters. Two more parameters, meaning FC dash and AC. Now FC dash, let's get the FC dash. FC dash equal to, I think F12, F11 has a FC dash. You come back here, and I think somewhere here on the appendix H, H 2.1, F11, you have FP dash, FC dash is equal to 22 megapascals. Compression parallel to grain. I think they just always parallel to grain, so we just mentions this 22 F11. So we have a 22 megapascals coming from table number H 2.1, and that is for F11. AC, that net area allowing the unfilled horns only. So let's say you have these cross sections, you remember 172 by 47, because we're going to take a on seasons, and this hole will be filled, right? Because you always have bolt inside that one. So we're not going to use the net area, we will just going to use the filled one. So you have 172 times 47, it gives me 8080 millimeter square. Now in that case, let's do the final one. NDC equal to 5 K1 K4 K6 K12 FC dash AC. I think the 5 we use how much? 0.7, 0.57 K1. So 0.7, 0.57 K1, K4. Let's read K4 and K6 together. K4 1 and K6 1. So K4 1, K6 1, K12 is 0.221, FC dash 22, AC dash 8080 millimeter square. In that case, you can calculate one is 15674.7 Newton, which is 15.6 kilonewtons. Now then you can just compare with N star if it is given. So NDC, which is 15.6 kilonewtons, let's say N star given is 11 kilonewton, then greater than N star, it's not given, I'm just making it up, then the column is adequate for compression strength. So that's the overall pictures.